In this lecture, we are going to talk about the quantum numbers. Now, what are the quantum numbers? Now, the quantum numbers are numbers that are used to describe the behavior of an electron. Now, we said that the electrons are better found in a region in space called the atomic orbiter, right? The atomic orbiter is the region in space where there is the highest probability of finding an electron. Now, there was a scientist called Erwin Schrödinger. In 1927, used his equation, which is famous, or which is called the Erwin Schrödinger wave equation, is a wave equation, to explain the probability of finding an electron about a particular region in space. And then from there, Erwin Schrödinger, from his equation, he was able to derive three quantum numbers. The three quantum numbers are, we have the principal quantum number. Then we have two azimuthal quantum number. Then we have three, the magnetic quantum number. Now magnitude, magnetic quantum number. Now there is a fourth kind of quantum number that were discovered by two separate scientists, but not by Erwin Schrödinger, and that quantum number is called the spin quantum number. Now, each of these quantum number talks about the behavior of the electron in a particular region. Are we getting it? In a particular region in space. How does this electron behave? If you want to describe the behavior of an electron, we assign specific or discrete numbers to them, which we call them the quantum number. Are we getting it? You know what we talked about quantum the other time, right? That when energy is being emitted, right? That we said that it is not continuous, but it's in packets. It's in discrete energy, or it's a packet or bundles of energy that we call the word quantum. So we assign specific numbers to them. These specific numbers that are used to describe the behavior of electrons in an orbiter is what is called the quantum number. So what is called the word quantum number. Now I said Erwin Schrödinger gave three quantum numbers, which are the principal, the azimuthal, and the magnetic quantum number. Now the principal quantum number, the azimuthal quantum number, is also called the subsidiary, in some places they call it the secondary, after principal, secondary, and then in some places they call it the angular momentum quantum number. Okay, the angular momentum quantum number. So you may see it as azimuthal quantum number, you may see it as subsidiary, secondary, or angular momentum quantum number. So at every point in time, any of these names can pop up. Okay, so having discussed the four kinds of quantum number, now what are these quantum number talking about? Like, what do they actually describe? Are we getting? Now let us take the first one here, which is the principal quantum number. Let's explain what the principal quantum number is all about. So we have here the principal quantum number. Now the principal quantum number talks about the energy level, or the shells. It talks about what? The energy level or the shell. Now it is designated with small letter n. Are we getting it? It is designated with small letter n, and small letter n has values corresponding to each of the shell. Now for your level, we are going to look at four shells, which are the K, the L, the M, and the N shell. And then we have N. The values of N that are actually that K can have is 1, that L can have is 2, that M can have is 3, and that N can have is what? 4. Let's take note of this, okay? The values of N that each of these shells can have, that's why we say they are quantized. That means they have only allowed or permissible values, okay? That's the meaning of quantized. We have only allowed or permissible values. So the principal quantum numbers talks about the energy level or the shells. And these shells are divided into 3. We have 3 shells. We have the K, the L, the M, and the N shells. And they have values of N is equals to 1, 2, 3, 4. Now, when we talk about the idea of energy level, the first thing that should come to our mind is the Bohr atomic model. Here we said we have the central nucleus and then we have energy levels, right? Can you still remember that we said this middle here is positively charged, and then we have electrons here. This first shell here is what is called the L shell. This one is what is called the M shell. This one is what is called the what? N shell. And then finally, this L, this K, sorry, the first shell here is K, not that. So we have something like this. And then finally, another like this. So this first shell here is called the K. This one here is called the L. Here is M. And here is what? N. And it continues like that. Now the K shell is the one closest to the nucleus. Hence, it has a lower value of N. That means it have a lower energy level. The ones further from the nucleus have a higher energy level. And then we assign what? N is equals to 4 to them. Is that understood? So that is what the principal quantum number is talking about. It describes the energy level. It describes the shell. Are we getting it? Now, you may be asked in the exam that when N is equal to 1, what shell are we talking about? Maybe asked when N is equals to 1, what shell are we talking about? Of course, you know we are talking about the K shell, okay? Talking about the K shell. Now, you may be asked when N is equals to 4, what shell are we talking about? The N shell, capital letter N. Are we getting it now? So that is for the principal quantum number. It talks about the energy level or describes the shell to which an electron belongs to. Now, an electron, or let's say the quantum numbers, can be what they describe can be likened to the layers in an onion, or the layers of the rooms in an onion bulb. Now, an onion bulb is something like this, right? Bulb, rather. You have the first one, then you have the second one, right? Then you have the third one, you have the fourth one. Now, don't look at this to understand what I'm trying to explain. Now, we have all these, right? Now, each of these rooms represent the quantum number and what they tend to describe. Now, the outer layer can be seen as the principal quantum number. Are you getting it? This one can be seen as the principal quantum number. And this can be seen as the shell, okay? Now, in the shell, we have what is called the orbitals. And then we have what is called the suborbitals. And then we have where the suborbital is where the electron is. And inside the suborbital, we have that the electron can spin in different direction. Now, talking about the principal quantum number, we've round up with the principal quantum number. We said it talks about the energy level of the electron. Okay. Now, let us look at the second quantum number, which is the azimuthal, or we can call it angular momentum, or we can call it subsidiary quantum number. Now, what is this one talking about? This one is talking about the sub-energy level. Sub-energy level. It describes the quantum number or the electron into its sub-energy level. Now, these sub-energy levels are called orbitals. Now, this quantum number also talks about the shape of each of these atomic orbitals. The shapes of the atomic orbitals. Now, the atomic orbitals are, we have the s, p, d, f. Now, another thing that we also need to know is this subsidiary quantum number is designated with small letter l. So, in quantum numbers, wherever you see small letter l, know that we are talking about the azimuthal or subsidiary or angular momentum quantum number, right? So it has small letter l, designated with small letter l. Now we said the quantum number, the reason why we said they are quantized is because they have permissible, they have allowable values. Now, what are the quantized values or the allowable value for the x, the p, the d, and then the f orbital? Now you agree with me that the s orbital has allowable value of 0, p has allowable value of 1, d has allowable value of 2, and f has allowable value of 3. Now, each of these values have a relationship with the principal quantum number, which we've discussed before now. So the principal quantum number is designated with n. So relationship between, let's look at that. The relationship between n and l. Now we said n is the principal, l is the azimuthal. Where's the relationship? Now the relationship is that l is equals to n minus 1. Are you getting it now? L is equals to n minus 1. So we can say that n is what? L plus 1. Because if this one crosses to this side, it becomes positive. So this is the relationship between the n and l value. So you may be asked, if n value is equal to 1, what are the values for l? So you come here and say l will be equals to n minus 1, and l is equals to 1 minus 1 is what? 0. Is that understood? So now if n is equals to 4, what will be the l value? The l value will be n minus 1, and l value will be 4 minus 1. L value 4 minus 1 is what? Is 3. Are you getting it now? So we are going to look at all this, and that is the reason why when you are writing your electronic configuration, when we look at electronic configuration, you understand this relationship better. So the atomic orbitals we say we have s, p, d, and f, and they are represented with l, small letter l, and they have value of 0, 1, 2, 3. And this one talks about the sub-energy levels, which are called the orbitals. Now the orbitals, they have various shapes. We have the s orbital. Now the shape of the s orbital is spherical. We have the p orbital. The shape of the p orbital is dumbbell. Then we have the d orbital. Shape of the d orbital is double dumbbell. And then we have the f orbital. The shape is complicated. That's a complicated shape. Now, what is spherical shape like? It's like something like this. This one has spherical, like a circular shape, but not that circular. This egg-like shape. Then the p orbital is dumbbell. Dumbbell looks like two spherical shape, right? Something like this. This is how the dumbbell look like. Then the d orbital is dumbbell, something like this. We have two dumbbell linked together. That is why we call it a double dumbbell. So when you see something like this, know that we are talking about the s orbital. Then this is p orbital, and then this is d orbital. Now we said the shape of f orbital is complicated. So this is what the azimuthal quantum number is all about. It talks about the sub-energy level or the atomic orbitals. Now each of these atomic orbitals, they have the maximum number of electrons they can accommodate. Are we getting it? They have the maximum number of electrons they can accommodate. The maximum number of electron is the x orbital can take a maximum of 2. the p orbital can take a maximum of 6. The d orbital can take a maximum of 10, and then the f orbital can take a maximum of 14 electrons. Now, having looked at the second quantum number now, which is the azimuthal, let us go straight to examining the third quantum number, which is the magnetic quantum number. Now, the magnetic quantum number talks about the orientation of the electron in a magnetic field, or the behavior of the electron in a magnetic field. Now, it is designated with m, small letter m, subscript l. It is designated with small letter m, subscript l. Now, what is its function? It describe, or let us say it's actually describe the behavior of the electron in the suborbitals. So it divides the electron into suborbitals. Let's take it like that. Into suborbitals. So you see that it has a link from up to down, from the highest down. So the first one we talked about was the energy level, which is the shell, like the onion I was telling you about. Then from the shell, what do we have? We have the orbitals. From the orbitals, what do we have? We have the suborbitals. Right? And then from the suborbitals, what do we have? We have the spin of the electrons in these suborbitals. Now, talking about the shell, we said is for N. Orbitals is for L. Now, the suborbital now is what we are looking at, which is ML. Now, ML has values ranging from minus L through 0 to plus L. Now, what does this mean? It means that the value of L is what determines the value of ML. From minus 0 through 0 to minus L, rather, through 0 to plus L. What do I mean by that statement? Start from minus L, then you'll be counting it down like the number line, right? For instance, you have 0 here. Now, let's say this is minus 4. This is minus 3, minus 2, minus 1. Then here will be 1, 2, 3, and here is what? 4. Okay? And then we'll start. If L is, let's say, 3, it means here will be minus 3, right? Minus L. That means you have to count from minus 3 to what? Plus 3. That means if L is 3, in a situation where L is equals to 3, okay? So, for instance, the case we are looking at before. So this will be minus 3. Are you getting it now? The values will range from minus 3, then you have minus 2, minus 1, through 0. Then we have plus 1, plus 2, and what? Plus 3. These will be the values for the magnetic quantum number. So it's usually from minus L through 0, not minus L, 0 and plus L, through 0. You have to follow this number line pattern, okay? So if the value is, let's say, minus 2, what do you think it will not be? It will be from minus 2, 1, 0, plus 1, plus 2, and plus 2. It will end there, okay? So that is for the magnetic quantum number. Now, there's a relationship between the magnetic quantum number and the one that directly comes before it or precedes it. The one that precedes it is the what? Is the azimuthal, which has L. So we say relationship between L and ML. Now the relationship is ML is equals to 2L plus 1. Okay? ML is equals to 2L plus 1. So if the value of L is, let's say, 2, if you substitute it here, ML will be equals to 2 bracket 2 plus 1. And this will be 2 times 2 is what? 4. Plus 1 is how many? 5. Now, this tells us the amount of suborbitals that will be present in a particular orbital. That was what I was trying to explain the other time, that the p orbital has how many suborbitals? We said 3. How? Let's now practice it. So we have the s orbital, we have the p orbital, we have the d orbital, and what? F orbital, which is what we got from here. We said the s orbital has 2. Okay, this one is talking about the maximum number of electrons. We are going to know the maximum number of electrons that they can accommodate from here too. Now listen, s orbital has just 1 orbital. Now why do we say it has just 1 orbital? Let's use this relationship here between m and ml. Now what is the L value for s orbital? Let's take the L value for each of the orbital. We have sp, this is sp df. L is 0, 1, 2, 3. Now, at the end of the day, our ml would be equals to, so for s orbital, our L value is what? 0. So this gives us 2 brackets 0 plus 1. 2 times 0 is 0, plus 1 is 1. Now, this tells us that the s orbital has only 1 orbital, which can be written as this. So it has just 1 orbital. Now, let's go to the p orbital quickly. Now for the p orbital, our L is 1. So we have 2 brackets 1 plus 1. 2 times 1 is 2 plus 1 is 3. So p orbital has 3 orbitals, which is this, which is 1, sorry, not the electron. Then we have the next one is the d orbital. For the d orbital, L is equals to 2. Now, if L is equals to 2, it means ml will be equals to 2L plus 1, which is equals to 2 brackets. L is 2, right, for d orbital. So 2 times 2 is 4, plus 1 is what? 5. So it means that the d orbital has 5 suborbitals. So if you have this as a d orbital, it means you have to divide this into 5. 1, 2, 3, 4, and 5. And then the f orbital, L is 3. So if L is 3, this becomes 2 bracket 3 plus 1. 2 times 3 is 6, plus 1 is 7. So the f orbital has 7 orbitals, which are 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, and 7, like that. Okay, so that is the relationship between L and ml. So you see that from your ml value, you are able to get, from your L value, you'll be able to get your ml value. Are you getting it now? Now, each orbital, take note, right? Each orbital can take 2 electrons. What we mean by that statement is each of these orbitals you see here can take 2 electrons each. Each of these buses you see here can take 2 electrons. So the 2 electrons must be spin opposed. So we have 1, 2. So the s orbital can take a maximum of how many electrons? 2. P orbital, you have 1, 2, 3, 4, 5, 6. So this one can take a maximum of 6 electrons. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this one can take a maximum of what? 10 electrons. Then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this one can take a maximum of 14 electrons. Now, by just looking at these values here, you'll be able to predict ml value. Let's come here now. We say these are ml values. ml values will be what? For s orbital is 1. For p orbital is 6. For d orbital is 10. And for f orbital is 14. Sorry. Not. For p orbital is 3. D orbital is 5. And then f orbital is 7. So multiply ml values by 2. What is it going to give to us? 1 times 2 is 2. 2 times 3 is 6. 5 times 2 is 10. And then 7 times 2 is 14. So this one now gives us the number of electrons that each of the orbital can accommodate. So each orbital can take 2 electrons. Now, having known all this, haven't known all this. Now the p orbitals, we said we have 3 suborbitals. The 3 suborbitals are ps. I think this is the one that at least should be acquainted to by now. Py. Oh, you get away. And then we have and then we have pz. Okay, then the d orbitals, we have dsy, dyz, dsy, and then just like that. But that one, I don't think for your level you don't have to actually know about this. Just do ps, py, and pz. Okay, so that is for the atomic orbitals and the magnetic quantum number. So now let's look at the next quantum number. Now the last but not the least quantum number that we are going to look at is the spin quantum number. Now this quantum number was not derived from the solution of the Schrödinger wave equation, and it is designated by m subscript s. Now it talks about the spin orientation of the electron in space. Now the electron can spin in 2 directions. Now if it spins upward like this, it has values of +½ However, if it spins downward like this, it has values of -½ So that's basically everything you need to know about the quantum number. And no 2 electrons in an orbital must have the same spin. What I mean is, for example, let's say you have these atomic orbitals. Let's say this atomic orbital is the p orbital divided into 3. Now no 2 electrons in this particular orbital can spin like this. If you do this, this is wrong. However, if you do this, this is correct. So they must spin opposed. Here one value is taking +½ and another value is taking -½ So that's basically all for the quantum numbers. Now let's note something. The total number of orbitals in a shell is given by the formula n square, and then the total number of electrons in a shell is given by 2n square. So if you are asked, recall that the shells, we have their n values. We have k, l, m, n. Are you getting it? And their n value is 1, 2, 3, 4. Now if you are asked how many electrons are in the n shell, how many electrons are in the n shell, what will be your answer? Now we said total number of electrons is given by 2n square. Now the n shell has n value of 4, so small letter n is 4. Now substituting into this equation, this gives us 2 bracket 4 square, which is 2. 4 square is what? 16. 2 times 16 is 32. So in the n shell there are 32 electrons. Okay, there are 32 electrons in the L shell, in the N shell rather. Now, if I give you, okay, the assignment I'm going to give to you now is how many electrons are in the L shell? Assignment. Let's take that. Assignment. Do this for me. 1. How many electrons can be accommodated in the L shell? That's assignment number 1. Now, assignment number 2. How many electrons are in the sublevel are in the sub level, okay, for which L is equal to 2, you know how to calculate total number of electrons. From the formula, you know what to do. Go through the video, you understand better. Okay, using this magnetic quantum number, when L is equals to 2, you know the total number of electrons that can be accommodated. Okay, so that is your assignment, and that brings us to the end of quantum numbers. We are going to do more later on that quantum number. Thank you very much for your time.